the University of Washington in Seattle. And the title of his presentation is Regime Shift in Arctic Ocean Sea Ice Extent. Harry?
Thanks. Let's see. All right, can everyone see the screen that says Regime Shift in Arctic Ocean Sea Ice Extent?
Yes, very good.
Okay. So that's the title, Regime Shift in Arctic Ocean Sea Ice Extent. And this was recently published in Geophysical Research Letters. So what is a regime shift? It's an abrupt, substantial, and persistent change in the state of a system. That's according to a paper by Reed 2015, and I think that's a pretty good definition. So let's look at Arctic sea ice extent, the full annual cycle. March is on top in blue there, and September is in red on the bottom. And we are going to focus on September. So usually the way you'll see it depicted is like this. The blue dots are the annual September sea ice extent in millions of square kilometers, and the red line is the least squares fit. And it seems to be pretty good. It looks like there's a downward trend and there's some variability about the trend. But if you look at the same data, let me take away the line, and let's look at the change from 2006 to 2007, which was, let's see, can you see the arrow that's on the screen? Does
Yes.
that work to use as a pointer?
Yes, that's fine.
All right.
Yeah.
So 2006 is up here at this arrow, and then there's a huge drop to 2007. It's the biggest one-year drop in the time series. And you'll see that after 2007, this September sea ice extent never recovered to its previous values. It's always stayed below the level that it was before 2007. So let's follow up on that by putting lines on the graph like this. So now it makes it look like there's a downward trend from the beginning in 79 through 2006, and then a period of no trend since 2007 with substantial interannual variability. And, so in my paper, I went through some statistical arguments just to show that, this is a statistically significant shift. That's the message, really. So, okay, let's look at a couple other papers. This one on the left, it's called Regime Shift in Arctic Ocean Sea Ice Thickness. So I stole the title of my paper from this paper from 2023. I figured, all right, if there's a shift in the sea ice thickness, there's probably a shift in the sea ice extent. So then I went looking and I found it. So what Sumada et al. Looked at the sea ice thickness distribution using upward-looking sonar data from across Fram Strait. And of course, most of the ice in the Arctic eventually gets flushed out through Fram Strait. So they're able to plot distributions of the sea ice thickness. And in the bottom left, you see that from 1990 to 2006 the distribution is in blue, and then 2007 to 2019 in orange. And there's a shift towards thinner ice. The mode shifts to about a meter thinner and higher. Now, I'm not the first person to notice that there was a period of no trend in the sea ice, September sea ice extent. This paper on the right by Igor Polyakov, his figure 1b is essentially the same thing as the one I showed a minute ago, with the September sea ice extent in blue and this broken red line showing the decline before 2007 and the period of no trend since 2007. So I think my only contribution was a sort of a statistical analysis showing that there's some significance to that to that shift. So the more interesting question is why? Why has there? Well, let me back up a little bit. I think it's well known why there was the big drop from 2006 to 2007. 2007 was a record low at the time, and there were many papers written about it, and it had to do with a big flushing of multi-year sea ice out of the Arctic, and that's pretty well established, and I'm not going to talk about that. But the more interesting question is, why has there been no trend since then? Um, so I will just go through some various papers that have touched on that topic. And I don't know, I can't say which is right or which is wrong, but let's just look at, first of all, let me look at the paper on the bottom by England et al., Mark England, which is still, as far as I know, still in review. It's been submitted to Geophysical Research Letters, but they wrote a paper called Surprising but Not Unexpected Multi-Decadal Pause in Arctic Sea Ice Loss. They looked at CMIP5 and CMIP6 models, and they found that multi-decadal pauses in Arctic sea ice loss in the face of global warming are not unusual. They occur, I don't know, I think he said 20% of the time or something like that. So I, I guess we should be surprised, but it's not unexpected. I don't really understand what the title, but I think the point is that these multi-decadal pauses do occur, and we shouldn't be too surprised about it. Um, so yeah, and then this paper by Baxter says that interdecadal variability of Arctic atmospheric circulation has contributed to slower declines in recent years, resulting in the appearance of a slowdown over the past 11 years. So sure, it's plausible that even with global warming continuing and the Arctic warming faster than the rest of the globe, you can still have a period of no trend in the sea ice just because of internal variability. So, but let's look at what some of the reasons might be for that internal variability. Internal variability doesn't just mean like random and we can't explain it. Like ENSO is internal variability, we can explain that. So what's going on? Well, this paper from 2020 suggested that when there's an early spring snow melt across the high latitude land areas, that leads to an abrupt atmospheric shift in the late summer, and that leads to reduced transport of sea ice through Fram Strait, which leads to a slowdown in the loss of sea ice. Ed Blanchard has a paper out, I think it's probably published by now, about boreal forest fires and how forest fires add more aerosols to the atmosphere, which means there's more scattering of incoming solar radiation, which means reduced warming, which means reduced sea ice loss. And the CMIP6 models don't use a realistic, don't have realistic forest fire modeling. So that could explain to some extent the pause in sea ice loss. We could look to the ocean. This paper from 10 years ago is about predicted slowdown in the rate of Atlantic sea ice loss. So 10 years ago, this was predicted. And it has to do with ocean heat transport anomalies, and that a spin down of the thermal highland circulation will continue, and this will result in near neutral decadal trends in Atlantic winter sea ice loss in the coming years. So there's a prediction from 10 years ago. And more recently, this paper from 2023, weakened Atlantic meridional overturning circulation diminishes recent Arctic sea ice loss. So the weakened circulation reduces the northward Atlantic heat transport, which means less basal melting, which means less sea ice loss. Then there's the Polyakov paper that I mentioned earlier from 2023, which is really about fluctuating Atlantic inflows, but it also pointed out this pause in September Arctic sea ice loss. And they talk about the Arctic dipole, which is the second mode of sea level pressure anomalies, and that this Arctic dipole has been in a positive phase since 2007, and this has caused a transfer of fresh water from the Siberian shelves to the Amerasian Basin, which increases stratification in the ocean, which suppresses upward heat flux, which allows for more sea ice growth, allows sea ice to grow thicker. So there's a hypothesis. There's also the Arctic oscillation could be doing something. It's been in a positive phase. I'm gonna skip the Arctic oscillation for now. Sea ice, there could be feedbacks in the sea ice. This paper by Jinlun Zhang in 2021, recent slowdown in the decline of Arctic sea ice volume. There's been a strong decrease in ice export, but only a weak decrease in the net ice production because of these negative feedbacks that thinner ice grows faster than thicker ice, and thinner ice diverges more easily, which leads to more open water, which leads to more ice production. So there could be these feedbacks in the ice cover itself that lead to the slowdown in the loss of sea ice. Then we can look explicitly at feedbacks. So let me go back to 2005, a paper by Ron Lindsay and Jinlun Zhang, where they were looking at the reasons for the sea ice loss in 1989. And they hypothesized that there was a preconditioning where the ice was getting thinner prior to this triggering event, and this large AO, positive AO triggering event in 1989 that flushed out a lot of thick ice. And then after that, the ice albedo feedback amplified the loss. And so this picture on the left just shows some of the positive and negative feedbacks in the ice. I think I've circled the negative feedbacks here. So why hasn't this happened? Why hasn't the ice albedo feedback kicked in and continued to reduce the September sea ice extent? Well, I don't know, but this paper from Geophysical Research Letters in 2011 says that the lasting impact of the ice albedo feedback is not possible because the large-scale heat fluxes quickly adapt to release the excess oceanic heat from the Arctic. So maybe there is no long-lasting impact of the ice albedo feedback. So back in April, there was a workshop here in Seattle of the Consortium for the Advancement of Marine Arctic Science. And I gave essentially the same talk at that workshop. And there was some discussion about whether models capture this period of no change in September Arctic sea ice since 2007. So we decided to, we had a breakout group on this topic, and we decided to follow up and just try to look at models to see if they capture this regime shift. So in table 1 in the lower left here, I've actually listed 4 regime shifts, all occurring in 2007. The first one is the sea ice extent that we just went through. The second one is the sea ice thickness, which I talked about at the beginning, that Sumata et al. Noticed. There's also a change in the area of multi-year sea ice. This paper by Babb that talks about step changes in the area of multi-year sea ice, and one of the step changes was in about 2007. And then there's also a paper by Hall et al. In 2023 about a regime shift in the freshwater volume in the Arctic Ocean, where there was a shift in freshwater volume from the Russian shelves to the Beaufort Gyre. And so that may be implicated in the hiatus in the sea ice loss. So far we have just a few models signed up here to take a look. The tentative title of this paper is "Do Models Capture the Observed Regime Shifts in Arctic Ocean Properties?" And we have some interests from modelers. The table at the right shows 3 of the models with a few of their components. And so we've outlined this paper. We have not produced any results yet, but we've got the introduction written, and we're hoping to make some progress on this. And I think we're open to other participation in this effort. So that's all I have to say. That's the end. Thank you.
Thanks very much, Harry. That's a great overview. So if you have questions, you can raise your hand, or I suppose you could unmute and otherwise get my attention to ask your question. Just to warm up here. So Harry, there appears to be a slowdown in the trend for all months, but the summertime has this abrupt transition that you've shown.
Yes.
What would the reason be for that? I assume that's because of that the ice thickness is the main driver here, and that you get a change in the ice thickness that's going to result in a dramatic change for the extent for the summertime. But in the wintertime, you're still going to have a large area frozen with colder temperatures. Does that sound reasonable?
I don't know, but I have looked at the sea ice index for all the months of the year, and there does appear to be this possible regime. There's a regime shift in September. It looks like there might also be the same kind of signature in July, August, September, and October. But the other 8 months of the year, it does not appear as if there is this kind of drop that we see in 2007. The other 8 months of the year do look like they're more gradual and not this kind of shift with the hiatus since 2007. So so the answer is that it does occur in a few months of the year. The reason, I don't know.
Would this hiatus be evident in related Arctic geophysical, biological, biogeochemistry time series? I believe you do some work with polar bears as well. Is that right?
That's right. Yeah. Yeah, there was a paper by Mads Peter Heide Jorgensen, who he looked at sea ice in East Greenland, and he did find that he found a regime shift in sea ice in Southeast Greenland that coincided with a kind of a change in the biology down there. I can't give you all the details, but I can. I think I referenced his paper in my paper, and I talked about it briefly there. So yeah, there can be um, biological or biogeochemical consequences, I'm sure, yes.
Okay. Okay, so earlier this century, there was quite a bit of interest in the pause in global surface temperatures. So at the time, Lewandowski and co-authors wrote that this was within fluctuations around a longer term trend. And in their words, there was no evidence that it was a unique or particularly unusual phenomenon, and therefore essentially a canard. So for the sea ice hiatus, I think you're indicating that this period is particularly unusual, and that it's unique in the contemporary observational record, and therefore it has and that it has fundamentally changed some of the Arctic physical characteristics. And so it's different. It should be viewed as different than what was looked at with the global surface temperatures. Is that fair?
Sure, I guess that's fair. I guess I would say that the paper by England and others have shown that you can have these 20-year periods where there's no sea ice loss, even in the face of global warming and the Arctic warming faster than the rest of the globe, because of this masking by internal variability. And internal variability, to me, it doesn't mean just random, unexplainable things. Internal variability can be explained, and that's what I tried to show in my talk, is that there's possible explanations in the atmosphere and the ocean and the sea ice and feedbacks that could explain this, and that doesn't mean, and it's sure this kind of thing, we shouldn't be surprised that it happens. It can happen from time to time, but we can also explain it, maybe. Um,
Yeah.
so I think it's all these possible explanations are totally compatible with the findings from the models that such a hiatus is possible.
Okay. Any other questions for Harry?
I have a question. This is Qing
Right.
Hua from UCSB. My question for Harry is that a very nice talk. My question is that can we learn something from the early warming, like 1940, something like that. Learn something that period to know better this recent hiatus in the Arctic. What do you think?
Yeah, I have not looked at the 1940s. I've looked only at the sea ice record, which included there was a big positive Arctic oscillation event in about 1989, that paper that by Zhang and Lindsay that I mentioned, where there was a similar flushing of multi-year sea ice, and that was also reflected in the paper by Babb, that there was a big flushing of multi-year ice in 1989. So this similar things have happened since 1979 in the sea ice record, but I have not looked back to 1940. No.
Thank you.
And Wilbert.
Yes, thank you, Harry. Great presentation. Thank you. I was wondering if you can talk a little bit about the CAMAS activity that you briefly alluded to. What kind of models are you inviting? I saw like a combination of fully coupled models versus maybe ocean sea ice models that are forced with atmospheric reanalyses. And maybe can you give us an idea of what kind of level of analysis you're requesting from the participating teams?
Sure. Yeah, we want to use models that we want to see if models can reproduce the drop in the sea ice extent in 2007. So in other words, they should use, realistic forcing that occurred, during the last, all the way through 2024, hopefully. I don't want to try to do another statistical analysis of whether this is plausible or not. I want to do an actual comparison of whether models are capturing what we actually observe or not. And so just looking at time series of September sea ice extent from models, looking at the sea ice thickness distribution, looking at, I guess models maybe don't distinguish between multi-year ice and first-year ice. I don't know, maybe they do. If they do, we could look at multi-year ice. So, simple time series of these things. And maybe Mike Steele would like to say something about that too. He was one of the organizers of the CAMAS workshop, and he knows more about these modelers and this type of activity. So, Mike, would you like to say something about that?
I think you've said it. I think that my experience with AOMIP and then Famous and now CAMAS is that the simpler the simplest focus is the best when you've got a many degrees of freedom, lots of different models and things like that. So, my interest is in focusing down for a paper. So for instance, on sea ice extent, perhaps only, or sea ice extent and sea ice volume, September only, looking at all the different models, trying to figure out how they're different and really digging into the details of how they're different. And as far as models go, Wilbert, probably, forced ice ocean models is what we're probably going to focus on to try to see if they can get 2007 or do they get 2008 for the shift or, things like that. Because there's a whole other question you can ask from coupled models, or do they get similar, runs of flat trend, and that's a good question, but it's a different question.
Thanks,
Thank
Mike,
you.
and thanks very much for the questions. Just finally, Harry, so as we said, there seems to be a decrease in the trend for all months, but it seems to be particularly large for September. So I guess that would suggest that the trend in an amplification of the seasonal sea ice signal has also paused. Is that true as well?
I'm not sure. I haven't looked explicitly at the annual cycle, but there was a paper that did look at the annual cycle, and I believe they did find a shift there, and I'm trying to remember what that paper was. But I think I referenced it in my paper. Yeah, I know I did reference it in my paper, and so I did mention that other researchers have found a change in the annual cycle. I just can't recall at this moment right now what that was.
Okay.
Yeah.
All right. Thanks, Harry. So let's now go to our second speaker. That will be Patricia DeRepentigny. She is an assistant professor in the Department of Geography, Environment, and Geomatics at the University of Ottawa. And she will be presenting on how predictable are the recent trends in Arctic sea ice decline. Patricia?
Yeah, thanks. I'll share my screen.
Okay, that's perfect.
Okay, perfect. Yeah, so hi everyone. I'm Patricia DeRepentigny, and yeah, today I want to talk about the predictability of the recent trends that we've seen in Arctic sea ice decline. And I just want to mention that most of this work has been done when I was a postdoctoral researcher at UC Louvain in Belgium. Okay, yeah, there we go. So Harry has nicely introduced this topic for me, and so you're going to see this figure again of the sea ice extent in September from NSIDC and the linear fit that you can put on top of it. Here, what I've done is I've added two other trends. These ones are 12-year trends, one that is kind of centered as the early 2000s, so up until 2012, where we've seen an accelerated decline in sea ice, and then the one since 2012 that is mostly flat. Again, these trends you can calculate them differently over different time periods, but the same message that we've seen before. And the pause in the sea ice decline that we've seen recently has given some fuel to some of the climate skeptics that have said that maybe we've been hiding the truth all along about what's happening in the sea ice. So there's been a lot of social media posts and articles saying that maybe we've kept this info out of the news because it doesn't serve the narrative. No, Arctic sea ice is not shrinking, and it has actually grown since 2012. We have been hiding this fact, and it's been continuing to recover since then. There's also this article here that shows this flattening of the trend since 2007, says nothing is melting anymore. That's their view, I guess, and other things like ice is rebounding at both poles anyways. And so one way to, have we really been hiding the truth? And so one way to kind of look at this is how unusual has this hiatus been? And so if we come back to this figure, the first question that we were asking is how unusual is this accelerated decline, and then the relatively stable conditions that followed. And there's this nice paper by Swart et al. In 2015 that looked at this question. They looked at trends in observations in a large ensemble, as well as in CMIP5 models in gray. And here they looked at, I'm assuming you can see my mouse again, like it was for Harry. Okay. They've looked at 7-year trends on the left, 14-year trends in the middle, and then 35-year trend on the right. And they've shown that for 7-year and 14-year trend, it is possible to have positive trends and highly negative trends, and that the observed trends are well captured by these models. But then when you look at the full observational record, which at the time was 35 years, all the trends are negative. And that's because the influence of internal variability starts to diminish and the force trend really starts to emerge. And so I've done a similar figure now with the trends that I've shown you before, and for CMIP6 models. And unsurprisingly, we get the same answer. And so for those 12-year trends that I've shown you before, the one in pink and the one in cyan, those are within the range of internal variability in terms of 12-year trends that we see in CMIP6 models. But again, when we look at the full observational record, which is now 45 years, the trends are all negative. There's also this paper that Harry mentioned, the paper by England et al. That is currently under review, that looked at CMIP5 and CMIP6 models and found that across all simulations, there's about 20% of them that show a 20-year trend that is larger than what we've observed in the past 20 years. And they've also accounted for different selection criteria based on equilibrium climate sensitivity or a reasonable sea ice area and found a similar number. And so if we come back to our question, how unusual is this? Not so unusual when you account for internal climate variability. And so we were like, great, but then if it is not unusual, then how predictable were these two periods of highly negative and neutral trends? And to do that, we can't expect uninitialized, fully coupled climate models to get, the 2007 loss in 2007 just because of random variations in internal variability. And so to kind of address that, we decided to look at simulations from the DCPP, or the Decadal Climate Prediction Project. And so this is part of CMIP6. And the models that participate in this effort, they submit simulations where they initialize the state of their model every year, usually around the fall. So you can see the dates here in the middle of the table. It's usually varying from October to December based on the model. And then they use various techniques and data sets, which are shown here at the right end of the table, to initialize their model to bring it as close as possible to observations. And then they run it for 10 years in the future. And so you can see here all the models here that we've that have participated in this effort and that we've been able to look at. Most of these models have at least 10 ensemble members, even some have 20. So that's great because it allows us to sample the effect of internal variability, at least to a certain extent. Okay, so the first thing we wanted to look at is if initialization helped fix the mean state bias. And what I mean by this is that you can see the 11 models here that we're looking at. This is the time series of September sea ice extent. In black, you have the observations, which is the same across all the panels. And then in blue, you have the uninitialized historical SSP CMIP simulations for all these models. You can see that some of them have quite a big mean state bias. For example, this CMCC model here has basically no sea ice across the observational record, which is kind of weird. And the North CPM model has way too much sea ice in September. And then the others kind of vary depending on the model. And so what does this look like in the decadal runs? And so those are shown in red. And here I'm showing you for forecast year 1. And so what I mean by this, and you can see this in the bottom corner here, bottom right corner, is that those models are initialized in the fall around November, and then we're trying to predict the following September. So this is like about 8 to 11 months later, post initialization. And what you can see is that for some of them, it actually helped quite a bit fix the mean state bias. Like for CAN-ESM here, we get something that's closer to observations. The ESM as well. It also helped for this CMCC model, although maybe that wasn't too hard. And you can see that there's still, even in this CMCC model, there's there's less sea ice than there should be. But then there's other models where it didn't change much. This IPSL model, the mean state is pretty similar to the uninitialized runs. And then there's some other models where like the HADGEM model here, where the mean state bias was positive, and then it kind of went the other way around, and now we have a negative bias that is larger than it was before. So, it's a little bit of a mixed bag. I think in general, for most model, initialization did help to fix some of the mean state bias. So that's somewhat promising. Now, let's look at the anomalies, kind of remove that mean state bias component and see if we're able to gain some insight about if these models are able to capture the varying degree of anomalies that result from the forcing. And so here I'm showing you, again, September sea ice extent anomalies. I've put a 3-year running average to kind of smooth things out a little bit. And what we're looking at is there's this period here around in the observations around 2007, 2012, where the anomalies are really large and have increased, and then this period that is more stable. And what we found, again, this is at forecast year 1, so just 8 to 11 months after initialization, we found that most models actually struggle to capture the strong decline that we've seen, like those extreme sea ice lows, like the 2007, 2012 sea ice minimums. But then they actually do a pretty good job at simulating the anomalies in the following years that we've seen since. You can ignore the CMCC model. Again, I've shown you before that it's kind of a little bit unrealistic, but you can see that for most of these models, it's really the extreme minimas that are hard to capture in terms of anomalies for these models. I will also point out that the IPSL model over here is actually doing a really good job at predicting when the anomalies become highly negative and then when they stabilize. However, this model, the last year of initialization is 2016, so we're not really able to kind of look further into the more recent years to see if that continues. But maybe there's some potential for some of these models to actually help us understand, and are they having the right mechanisms that lead to these anomalies that match well with observations. Okay, so let's come back to this idea of our trends. Now, if we look at 10-year trends, because these simulations are run for 10 years, that's kind of the maximum that we can look at. And here I'm just showing you, again, this distribution of 10-year trend in uninitialized historical simulation over the whole observational period. Now, if we look at that same distribution in those runs that are initialized, our decadal prediction runs, you can see that the distribution starts to widen. And so it seems that by initializing our system, we are able to get more extreme trends, so more highly negative trend and a lot more highly positive trend, which is interesting. Maybe that helps us understand these more extreme years. I will also add back the two trends that I've shown before, the one in pink with the accelerated decline and the one in cyan for the slowdown, and then show you the same distribution just centered over these specific years. If you kind of squint at this histogram for a minute, you might see that it seems like the pink distribution has a mean that shifts towards more highly negative trend, which would be, intuitive, given that these are the years where we've seen the accelerated decline, and that the cyan distribution kind of shifts to the right towards more positive trends. However, those distributions are not statistically different, and so you have to take this a little bit with a grain of salt. Now, we wanted to look at how this looks like in individual models, and are we actually getting more extreme trends for the right reason? And so this is showing you 10-year trends. Now we're taking not just forecast year 1, but the 10 forecast years for these models. And we're calculating the trend in September, the 10-year trend. And then on the x-axis here, I'm showing you the end year of that 10-year trend. So that last year of the trend. And what you can see is that first of all, there's two models that only have 5 years of simulation. So we cannot calculate 10-year trends, so hence no data here. But you can see that there's a few models, for example, ECR, GEM, and CSM2, that have positive trend over 10 years, which is kind of strange and not what we would expect. And that is partly because these models have a lot of drift. And so they do a pretty good job at forecast year 1, but then as we continue to predict in the future, they drift towards a state that is unrealistic. And actually, if you look at the trend over September, the sea ice is growing. So not a really good thing for us that are trying to look at these 10-year trends. I will highlight again that IPSL seems to be doing a decent job at capturing the increasingly negative trend and then the kind of slowdown afterwards. And it also seems to be doing better than the uninitialized run. So again, maybe this is a model that we can kind of dig into more to look at the mechanisms to see if this actually matches what Harry has seen in terms of volume, in terms of atmospheric patterns or things like that, and if this model is getting the right answer for the right reason. Okay, so just to recap, I've shown you that the recent trends in Arctic sea ice decline are not unusual when we take into account internal climate variability. The initialization generally improves the model ability to reproduce the evolution of September Arctic sea ice extent at 1 year lead time, especially in terms of reducing the mean state bias. Climate models seems to not struggle to represent the recent pause that we've seen at 1 year lead time, but they do struggle to capture the accelerated decline in the early 20th century. And so this suggests that those might have been unlikely events. And there's been papers that Harry has mentioned before that suggest that maybe this is due to some processes that are not adequately represented in the models, maybe some tropical polar teleconnections or things like that. And then predictability beyond a few years deteriorates quite quickly in some models due to model drift. So that makes it hard to assess more of the long-term predictability. However, this should not be very surprising. We know that sea ice has predictability up to a few years. And so we didn't expect to get good predictability up to 10 years when starting this research. And so I'll leave my contact information here and happy to take any questions.
Thanks very much, Patricia. So again, if you'd like to ask a question, just raise your hand or unmute and otherwise get my attention. Patricia, could you just go over again how the models were initialized? Did they use reanalysis? Did they use ocean reanalysis?
It varies a lot by model.
Okay.
They don't initialize, like some of them only initialize the surface of the ocean. Some of them initialize deeper into the ocean. They use different data sets. Sometimes it's reanalyses. It varies across the board. And so it makes it a little bit hard to say, like, have a coherent answer when doing this type of model intercomparison. A little bit like when Mike mentioned earlier, there's just a lot of degrees of freedom that you have to consider. And so this was just meant to kind of have a look at, because we have these simulations, right, that are being done, and like modeling centers are putting a lot of effort into that. And so we kind of wanted to see, like, are these helpful to answer some of these questions when related to Arctic sea ice, because they have been shown to be helpful to look at decadal predictions of other components of the climate system. But it seems that maybe for Arctic sea ice, it's a little more of a muted answer.
Chip Miller, would you please unmute and ask your question?
Yeah, thank you very much, Patricia. Hey, I was wondering if you might expect more model skill if the models were initiated or reinitialized with the mid-September information from the previous year, when you do expect to see the maximum open water extent.
Yeah, that's a very good question. There's some of these models that the protocol was to at least provide initialization in the fall to have, be able to kind of compare across them. There are some models that have done initialization at other months of the year. And for example, in May, and of course, when you initialize in May, you do get a better answer for September. That impact of initialization is still there more than if you initialize in November. But there actually wasn't much of a difference in the long term. After 1 year, most of that predictability is lost. And so, yeah, then it becomes a question of what do you choose to assimilate and how you decide to do it. Yeah.
Thanks for the question. Xinghua?
Patricia, very interesting talk. So my question is that if you try to see the model DCPP model, do you think the model can capture the drop from 0.6 to 0.7? That's a really fast drop if a model initializes in like the November of the 06, 2006.
Yeah, we
Have you-
haven't seen that. No, we haven't seen that they've been able to capture that largest year-to-year variation from 2006 to 2007.
Okay, thank you.
Yeah.
Now, related to this, we of course have a seasonal prediction system here, and there's been a lot of work looking at hindcasts of seasonal prediction systems. Even in state-of-the-art systems, which look back at hindcasts for 2007, 2012, they do terrible for those 2 years. So that would suggest that even with excellent initialization and very short time scales, they can't predict that. Do you have any thoughts on that? What are we missing?
Yeah, that's a great question. And I think that's kind of what I'm getting out of this as well, is that maybe the more recent years are kind of just following the linear trend, which models are adequately able to capture. But those highly extreme years are really what they struggle with. What is missing? That is a great question. I think and Harry has mentioned that in his talk. I think there's been work in the literature trying to look at that a little bit. I think maybe if there hasn't been this strong decrease in or export of really thick ice in the models around that time because of not adequate atmospheric circulation or ocean processes, then you might not be able to get the result that we've seen in 2007. Some work by Ian Baxter and Xinghua about teleconnections with the tropics and that are missing, or some of these processes that are missing from the models could also explain that. I think there's a few hypotheses there, but yeah, it does seem to be the case that we're not able to hit the mark on those 2 extreme years, and even in terms of seasonal predictions.
I think some modelers have suggested that it's like late season weather phenomenon and other things that can affect the extent, and therefore it's not predictable on seasonal timescales.
Yeah.
I think that might be a cop-out. I don't know.
Yeah,
Mike,
for sure.
your question.
Yeah, you were just talking about the predictability of what happened in 2007, but in terms of why it happened, Harry went through a list, and I was there in 2007, and as he mentioned, there were a bunch of papers written. Why did this happen in 2007? And I think Mark Suarez, there was a paper written. It was like the perfect storm. I mean, I think that this recent work by Harry and Patricia and others, where we're focusing on 2007 again, we're sort of refocusing on back to 2007, might help, but might be useful because I think we left that phenomenon and moved on, and what we did was we just decided that it was a bunch of different things, but that's not really satisfying, and maybe now we can go back and try to figure out what it really was. So that's what I'll say.
Yeah, I'm concerned that there might be a drop this September, and then we'll forget about the pause and all of this again because the trend has restarted. But we'll have to see. Thanks for the question. Thanks for the point, Mike. Another question, Patricia. So years ago there was a point that CMIP models were not matching the long-term Arctic sea ice loss. With this pause, is this a case of the observational record coming into being adjusted into better agreement with modeling results?
I mean, I think it's 2 things, right? I think we have more observations to compare to. We have a better idea of
The longer record.
The longer record. Yeah, exactly. I think our models are getting better, giving at a very slow pace and with like really small increments. But I think, and there's been work that I've been involved with the SIMIP community that has shown that when it comes to the response of sea ice to forcing or to temperature, we're actually doing better compared to earlier versions of CMIP. And so, yeah, maybe that could be. It's hard to say. I think for these uninitialized, models, fully coupled, they have a lot of issues, and also like kind of piling them together and taking that as a trying to make a coherent answer out of it is maybe not the best approach. But yeah, I think it's slowly, the picture is getting clearer with time for sure.
Any other questions for Patricia or Harry? So with a few minutes to go, Harry did bring up Stefan Jaeger's paper from 2015 in which he predicted a slowdown. He predicted that for the winter. Could either of you explain the difference then between what we're looking at in this recent period for the summer pause versus what Jaeger was indicating for March?
Yeah, I mean, I think so. Mark England's paper has shown that this pause, this 20-year pause, is present across all months of the year. Maybe it's not strong enough to qualify as a regime shift based on the statistical methods that Harry has presented. But I think there has been, according to this new study that is under review by Mark England, there has been also a pause in the winter. So that doesn't really contradict what Steve had found in 2015.
Okay. So Jaeger's paper strongly hinted on the role of thermohaline circulation and the overturning circulation. My discussions at the AMS polar meeting, I was strongly cautioned that there are many mechanisms that go between the AMOC and warm water intrusion into the Arctic. But just as a general question, we see this abrupt change from, a downward trend to a pause sometime in 2007, or as you showed in 2012. Would you expect the overturning circulation to act on those timescales, or is this part of the complex response then that occurs between those changes and what one might expect the response to be in the Arctic?
Yeah, that's a great question. I think this is more of like a slow buildup. I think there has been work though, like some of the work that we've done with the biomass burning that I've done with Ed and with previous colleagues at NCAR have shown that some of these type of forcers can result in a change in AMOC that can be quite sudden for AMOC timescales, in terms of like a few decades. And so that could be something that has been building up, since the early 2000s, like Steve was alluding to. Yeah, I don't know, Harry, if you have anything to add, but.
Okay.
No, I do on the topic of the monthly the change in the sea ice extent in each month other than September. Could I share screen again and just show a graphic?
Yeah, go ahead. Sure.
Let's see. Okay. Can everybody see the
Yes.
screen now?
Yes.
So,
and your cursor. Yeah.
Yeah. So these are, this is the sea ice index. I pulled this from NSIDC website, and I inserted the vertical red line at the year 2007 in every panel. So starting in the upper left and going down January, February, March, April. In January, February, March, April, May, June, I don't see a regime shift. I haven't done any statistical analysis here. I don't see a regime shift. I'm going to scroll up now to the later months of the year. So now we're looking at July, August, September, October, November, December. All right, September, we've all seen September. It looks like, there's a shift is plausible. July and August, it looks like plausibly there is a shift. It looks like July and August, there's probably been no trend since 2007. But once you get back to November and December, I don't see a shift. So that's all I have to
Yeah.
say.
Okay, great. All right. I'd like to thank the two presenters again for a lively discussion. I thought this was fantastic. Wilbert, what is next for our group?
That is a real good question, Richard.
I think we are on hiatus for next month. Is that right?
I think so, yes. We'll certainly follow up with the team about our
Okay.
next meetings.
Okay. Okay, we'll have new topics then for the fall. So until then, I'd like to thank our presenters again. I'd like to thank the audience for their questions. That was very, very useful. And thank you again. And so long.
Thanks, everybody.
Bye-bye.
Thanks, everyone.